Welcome back, AP Stat. This is part 2 of chapter 21. We're going to be talking about hypothesis tests for a two-proportion sort of situation. So just like last time, we're not just dealing with one proportion anymore. We're dealing with a comparison of two proportions. So to perform a hypothesis test for the difference between two proportions, we use the normal distribution model. The hypotheses for a two-proportion z-test are often these right here. Now, the folks on the left over here, these hypotheses, are often how it is written. Either the proportions are the same or they are different. Now, with a little bit of algebra, we can go from this side over to this side, and these folks look a bit different, and this is actually more true to what's going on mathematically. If P1 equals P2, then the difference is 0. If P1 is not P2, then the difference between P1 and P2 is not 0, okay? So this is more true to what's going on mathematically because we are analyzing the difference of proportions. We could see the following sets of hypotheses, though they are less common. We have the proportions being the same versus the first being greater, which would look like this if we were going to explicitly mention the difference of proportions. Or we could have the opposite, where the alternative hypothesis is P1 is less than P2, which would mean that the difference between the proportions is less than 0. These, however, are not terribly common. We're mostly sticking to up here. Assumptions and conditions are the same for those of a two-proportion confidence interval. So, the 2013 International Bedroom Poll, there's a survey group I've never heard of before, surveyed about 250 randomly selected adult residents in each of 6 countries and asked them about their sleeping habits. Sleep researchers generally report that, and I quote, people who regularly use their computers or laptops in the hour before trying to go to sleep are less likely to report getting a good night's sleep, ellipsis. More likely to be categorized as, quote, sleepy, ellipsis, and more likely to drive drowsy, ellipsis, than their counterparts. There's a lot that's not there, but judging by the 3 ellipses there, but you get the idea. The poll found that 28 or 51% of 251 U.S. respondents reported using a computer, laptop, or electronic tablet in the hour before trying to go to sleep almost every night. By contrast, 162 or 65% of 250 Japanese respondents made the same admission. Is this difference of 14 percentage points real, that is significant, or is it likely to be due only to sampling variability? So here's the question we need to answer. Is there a difference between the proportions of US and Japanese adults who use laptops in the hour before bed? Now, clearly the Japanese proportion is higher, but notice the verbiage. Is there a difference? That means that we are testing whether the proportions are essentially the same or if they are significantly different in one way or another. That would be a two-sided alternative. So, let's get to work. Assumptions and conditions. Independent groups. The two groups are independent of each other because the U.S. and Japanese respondents were selected randomly and separately from one another. Independence assumption, all right? The International Bedroom Poll selected respondents at random. They should be independent. Just to make sure, we want to check for randomization and 10% rule. Randomization condition was satisfied. The respondents were selected at random. 10% condition, the number of adults surveyed in each country is certainly far less than 10% of that country's population. We're talking about 2 of among the most populous countries in the world. And we have the success-fail condition. In the United States, 128 people used laptops before bed and 123 didn't. In Japan, 162 people used laptops before bed and 88 didn't. The observed numbers of both successes and fails are much more than 10 for both groups. All right, so we've met all of our assumptions and conditions. We have this independent groups assumption, and we checked independence using randomization and 10%, and our success-fail condition allows us to use a normal model. Very good. We will proceed to the two-proportion z-test. So here are our hypotheses. So, null hypothesis. There is no difference in laptop use rates between the two countries. We have the proportion from the US and the proportion from Japan. Difference would be nothing. Alternative hypothesis, the rates are different. We have the proportion of the US minus the proportion of Japan is not equal to 0. You don't need to necessarily write the first parts of these hypotheses. You would just need to say proportion of US minus proportion of Japan equals 0 versus alternative proportion of US minus proportion of Japan is not equal to 0. That's all you would need to write. And then we use the two-proportion z-test to find the p-value, and that is a job for your calculator. So let's get to work on the calculator here. We're going to go to Stat. We're going to go to Tests, and we're going to go to two-proportion z-test. That's number 6. Hit Enter. And then we need to enter our values here. So x sub 1, this is going to be the US group right here. We have 128 individuals that fit the desired characteristic out of 251 sampled. And now for the Japanese group, we have 162 who fit the desired characteristic out of 250. This is the correct alternative hypothesis. We go to Calculate, and we have a p-value that is very, very small. So how shall we summarize our result? The book says the p-value of 0.0017 says that if there were really no difference between the proportions of US and Japanese adults who used laptops before bed, then a difference as big as the one we observed would be highly unlikely, less than 0.2% chance. That is so small that I reject the null hypothesis of no difference and conclude that there is evidence of difference in the proportion of US and Japanese adults who use laptops before bed. It appears that Japanese adults are more likely to use them before bed than are US adults, and the only reason we can say that last sentence is that our sample proportion was greater for Japanese adults. However, technically our study was to determine if there is a difference, and so that is what objectively we are allowed to say. Though, of course, the Japanese rate was indeed higher, and significantly so. All right. Here's another problem. One concern of the study on teens' online profiles, and this is over 5 years old at this point, so if anything, it's only gotten more dicey in the online profile world, the social media world, was safety and privacy. In the random sample, girls were less likely than boys to say that they are easy to find online from their profiles. Only 19%, or 62 girls, of the 325 teen girls with profiles say that they are easy to find, while 28%, that is 75 boys, of the 268 boys with profiles say the same. Are these results evidence of a real difference between the boys and the girls, at least in terms of their online profiles being safe and private? Perform a two-proportion z-test and discuss what you find. Okay, so first and foremost, we need to check our conditions here. We're going to start out with our independence within each group, randomization. The sample of boys and girls were both chosen at random. 10% condition is clearly satisfied. We're going to look at independent groups. Now, are the groups independent from each other? Because the samples were selected at random, it is reasonable to believe the boys' perceptions are independent of the girls. That is an assumption. The thing with independent groups is you're looking for a clear violation, and we don't see any clear violations. We don't see matched pairs. We don't see pre-test, post-test, and offering a treatment the second time around. No. We don't see any of that. So we're looking for a clear violation, and there is no clear violation. All right, success-fail condition. Among the girls, there were 62 successes and 263 fails, and among the boys, 75 successes and 193 fails. These counts are at least 10 for each group, clearly. Because all assumptions and conditions are satisfied, it is okay to do a two-proportion z-test. Let's do it. All right, so here are hypotheses. The proportion of boys minus the proportion of girls is equal to 0 versus the proportion of boys minus the proportion of girls is not 0. And again, though the boys' percentage is higher here, we are looking for, I will remind you, a real difference. All right, so a difference one way or another is what we're testing for, so we're using a two-sided alternative. We're now going to use the two-prop z-test to find the p-value. Here comes the calculator. Okay, here we are. Let's get to it. We're going to go to Stat, go to Tests, just as before. We'll go down to number 6, two-proportion z-test, and now we got to enter our groups. The first group is going to be for the girls. That would be 62 out of 325. For the boys, we have 75 out of 268. 75 out of 268. Our alternative hypothesis is correct. We hit calculate, and we find a p-value that is pretty low. It's just a little north of 1%. So now we need to summarize our results. The p-value is very small, so I reject the null hypothesis. The study provides strong evidence that there is a significant difference in the proportion of teen boys versus teen girls who say they are easy to find online. Here are just some closing notes. We need to talk about the variability in the sampling distribution of one proportion versus two proportions because they are in fact quite different. Recall the standard deviation of p hat, the sampling distribution of sample proportions, is square root of pq over n. That is a fact that has probably been drilled into you at this point. Whereas the standard deviation of the sampling distribution of the difference of sample proportions is different, right? And notably, we include more proportions, so we need to include more variability. That is why we take the square root of a sum of proportions as opposed to just one. That becomes really important when we get questions like problem number 3. A February 2014 public opinion poll asked 1,000 randomly selected adults whether the U.S. should decrease the amount of immigration allowed. 36% of those responded yes. In June 1995, a random sample of 1,000 had found that 65% of adults thought immigration should be curtailed. To see if that proportion has decreased, why can't we just use a one proportion z-test of h sub 0 equals p equals 0.65 and see if the p-value for the sample proportion is really, really low, or this is not likely, but a high p-value. So we just analyze the p-value that way. Well, here's why. Since we have two samples, we have the 2014 sample and the 1995 sample, we need to perform a two-sample z-test because the sampling distribution for a single proportion and the sampling distribution for the difference of two proportions have different formulas for the standard deviation. So if we were to perform the hypothesis test described here, we would be incorrectly accounting for the variability of the difference of proportions. If you have two proportions and you are comparing them, you cannot use a one proportion z-test. You must use a two proportion z-test, all right? One proportion z-test, two proportion z-test, because the variability is literally quite different. So, number 4, for opinion polls like this, which has more variability? The percentage of respondents answering yes in either year or the difference in the percentages between the 2 years? Now, even if you didn't see the formulas, if you're dealing with one variable, there's one variable's worth of variation. If If you're dealing with two variables, you have two variables worth of variation, and variation always compounds. Variation always adds, all right? Regardless of whether you're adding variables or subtracting variables or whatever, you are always adding variability, okay? So the answer is the difference in percentages will have a greater variation. We simply have more variables. And if you look at the formulas, we have one proportion under a radical versus a sum of two proportions under a radical. We're going to have greater variability as we have a greater number of variables, regardless of whether we're adding or subtracting. And hopefully you will invariably complete this assignment. Have a great day.